and thank you for the nice introduction. So yeah, my name is Audrey Miniere. I'm a postdoc with Sabrina Spech and Karina von Schuckmann. I'm working in the Laboratoire de Météorologie Dynamique in Paris, but I'm based in Toulouse. And my subject is the ocean warming. So today I will present you some parts of my work about the estimation of the ocean warming, and we will discuss the challenges and the recommendation for ensuring its robust evaluation. So to understand ocean warming, we need to start with the Earth's energy imbalance. So today, because of our greenhouse gas emissions, we have more incoming solar energy entering the Earth system than the outgoing thermal energy leaving the system. So this causes a positive energy imbalance at the top of the atmosphere. And the main consequence of this positive energy imbalance is the accumulation of excess energy throughout all the different components of the Earth system. So with 1% of this excess energy stored in the atmosphere, 5% in the land, 3% in the ice, and all the remaining energy, which is 91%, is directly stored in the ocean. So this causes the ocean warming, and we can observe this ocean warming and also simulate it through observation and models by using this time series of ocean heat content. So here we have the time series of ocean heat content between 0 and 2,000 meters, and it shows that since 1960s, the ocean gets more and more energy, around 400 zeta-joule. And this warming will also continue in the future, even if we reduce our greenhouse gas emission. And this is due to the deep ocean warming, which is irreversible and committed for many years. So the ocean heat content is a very fundamental indicator for assessing past, present, and future climate changes. And today, we have a coordinated effort to estimate an ocean heat content time series at international level. Here, we in this figure, we have the ocean heat content for a different layer of the ocean. So it is the time series from the paper of von Schuckmann et al. 2023. These time series are fundamental because they are key indicators supporting international climate monitoring programs such as the Copernicus Marine Service, the WMO, and the GCOS, the Global Climate Observing System. So the question is, at which rate the ocean is warming today? And to get this rate of ocean warming, we need to compute the trend of the ocean heat content time series. And this gives us the rate. And here in this figure, I try to synthesize all the warming rates I found in the published papers. So each point represented in this figure represents one assessment of global warming rates. So for example, to understand better, we can refer to this group of blue points here, which are warming rates estimated over a long-term period of 60 years, indicated by these blue colors, and starting in the 1960s. So here it's very interesting because to see that all these values are positive. So this is this energy imbalance, positive energy imbalance. So traducing this heat accumulations within the Earth system. And more interestingly is that we have a large amount of estimates in the two last decades, since 2005, but we have also a large spread among estimates with different error bars, different value, ranging from 0.5 to 1 per meter squared. So the question here is why we have such discrepancies among these published estimates. And surprisingly, today we don't have established best practices in the literature for estimating these important ocean warming rates. So my question is here in this talk is how to ensure a robust comparison between different estimates of the ocean warming rates. So to answer this question, we need to go back to the formula of the ocean heat content. So the ocean heat content is expressed in joules, is an energy amount. And we can compute this heat content by with the integral of the seawater temperature over the ocean volume and multiplied by the seawater density and the heat capacity of seawater. So it may seem very straightforward as calculation, but in reality, this volume integral hides a very complex observational challenges corresponding to the evolving subsurface temperature observing system. Because we have observations since 1960s of the subsurface temperature, but in the early 1960s, we have mostly observation in the northern hemisphere, and these observations are limited to the first 300 meters of the ocean. Then in 1985, thanks to the XBT instruments, we have more global and complete coverage, but still with large gap in the southern hemisphere. And the profile also are limited to the first 700 meters. And since 2005, we refer this period as a golden era because we have a large amount of instruments and measure of these profiles, temperature profiles, and we have a near global coverage now, and mainly thanks to these Argo floats, which are this kind of this yellow instrument here, showing here. And now we cover the first 2,000 meters of the ocean. And to get a regular product from this irregular profiles, to get regular products which are more usable, easily usable, we need to do a large amount of methodological choices. So for example, we need to choose some instrument bias correction for this kind of instruments like XBT or MBT. We need to choose a methodology also to fill the gap. Also for the mapping, so the mapping refers to all the statistical method we have to interpolate these irregular temperature profiles to a regular grid. We also have this step of the selection of instrument type. If we just take Argo floats or more kind of instruments, there is also the important step of the quality control, how to select the best quality data, and also this climatology choice to refer to a temporal baseline. So this methodological choice have an impact on the final oceanate content estimates, and they are very well documented in these two studies of Boyer et al. 2016 and Savita et al. 2022. So each research group does its own choice, and this leads to a large amount of temperature products in the literature. So here I have a list of these different graded temperature products from in situ data. And I use this ensemble approach to compute the ocean heat content time series. So here in the figure, we have the ocean heat content for each member of the ensemble, with also the ensemble mean in the blue bold line, and the ensemble spread in shading. And from this ensemble, I could perform a sensitivity analysis to test the impact of on the ocean heat contents. And I present all these methods in a paper that we entitled the ocean component of the Earth heat inventory, but I will explain the title later. And the idea of this paper is to provide a methodology to estimate in the more consistent and robust way this ocean heat content time series. And at each steps of the calculation, and I ask myself some questions, which are, for example, which method I use to estimate the warming rate of the tendency of the ocean heat content, how I compute the uncertainty associated to this ocean heat contents, which value I use for the seawater density, the heat capacity, if, for example, I take it constant, or if I take it variables in space and time, which temperature products I use, and also which domain I use for computing this ocean heat content, because it's important to know that from one product to another here, they don't have exactly the same coverage. For example, the IAP products provide temperature in the global areas, but other products are limited. They exclude, for example, the polar areas or the shallow areas of the ocean. So they don't have exactly the same ocean domain, and we have to deal with this issue. So in this paper, I present the sensitivity analysis, and the next figure is the synthesis of all the sensitivity tests I performed. So I try here, each bar represents the tendency of the oceanate content that I computed over the period 2005 and 2020. And I test the sensitivity to the product. So here we have different value, but they are almost all between 0.5 to 0.7 watt per meter squared. Some products, for example, the purple one here, show lower value. But if we look at the error bar, they all agree. Here, the black point is the ensemble mean. Then I also do other sensitivity tests. So for example, the two here are the choice of temperature. So I try to take different definition for the temperature, the in situ, the potential, and the conservative one. So they differ from one another by the definition, most thermodynamic difference. So here we can see that in this test, it does not affect the tendency. The choice of the temperature does not affect the tendency of oceanate contents. Then we have also the sensitivity to the value of the seawater density and the heat capacity. And it's the same result when we take it variables or constant through time and space. It does not affect the tendency of the oceanate contents. And the two other sensitivity tests is the ocean domain and the trend method. So for the ocean domain, just look at the point here, which represents the ensemble mean, and the triangle is just for the individual numbers. So here, this test, I try to compute the oceanate contents on the product where I don't mask anything first. So this is the black points. And then I try different masks on my products. So the next point here in gray is a case where I mask the high latitude regions, and just to see if there is an impact. And the more extreme case is the red point here, is the case where I take the more common ocean volume through all my ensemble. So that is a more restrictive ocean domain I have, and it may impact the tendency here around 0.1 per meter squared. And the last test is the method I use to compute this warming rate. So here we have a list of different methods, published methods, and I use, for example, the least square regression, so two types of least square regression. I also try to smooth the time series of the oceanate content before computing the slope between the 2 points. And here is the result. So we can see that it does affect also the central estimate around 0.1 per meter squared, and also the error bar. But so here is the first time we do this sensitivity analysis, and it's important to do the sensitivity test to ensure this more robust oceanate content time series, and to keep in mind the sensitivity of each steps of the process. So I apply then this methodology to get my oceanate content time series, and from this ocean warming rates, we can then estimate the Earth energy imbalance. So this corresponds to the global warming rate, and we can do this with the Earth heat inventory. So it's the Earth heat inventory when we estimate also the heat content in the ocean, but also in the land, the ice, and the atmosphere. So this is the work done by Karina in our study in 2023. And it's currently the only way to estimate the absolute value of the Earth energy imbalance. So that's why we need a very robust methodology to estimate this oceanate content also. So today we have these two values for the Earth energy imbalance over the long-term era of 0.48 watt per meter squared and over the shorter period. But this time series ends to 2020. And the idea now is to extend the time series until the present and to provide an update of this Earth heat inventory. So our study, our methodological paper, will directly serve this international initiative to update the Earth heat inventory until the 2025, and to estimate this ocean component of the Earth's inventory. So so I will summarize now. So the oceanic content is a crucial indicator for understanding past, present, and future climate changes. And as we saw before, its assessment is very challenging because of the observing system evolution and this large amount of temperature products in the literature. So it requires a robust and consistent methodology, ensuring careful data processing at every stage. Here we use an ensemble approach because it helps us to ensure a reliable comparison across all these products and these oceanic content estimates. And we need a coordinated international effort to establish clear guidelines for and provide a reliable oceanic content indicator and addressing these critical aspects such as ocean domain, selection, product characteristic, etc. So last but not least, the ocean is warming, but this warming is accelerating, and that is the main result of our studies in 2023. And to estimate this warming acceleration, we need a robust oceanic content indicator. So when we estimate it consistently and robustly, the oceanic content is also fundamental to address this crucial question and alarming question of warming acceleration. Okay, so I finished my presentation. Thank you.